All right, welcome back, everyone. So let's start talking about the overall trends in ionization energy. So here, ionization energy depends on two different things that we've already talked about. First, it depends on the average distance an electron is from the nucleus. From nucleus. So remember, ionization energy, we're talking about the first ionization energy, is the amount of energy it requires to remove an electron from a neutral gaseous atom. So depending on how far away that electron is from the nucleus will affect its ionization energy. So we have to kind of think about those trends from the trends in radius from the previous slides. And ionization energy also depends on Z effective. So effective nuclear charge. So uh, in general, so if we put these things together, we already talked about ionization energy that we know going down a group, the outer electrons, it becomes easier to remove an electron. So it has a lower ionization energy, and that is because of our first dependency here, average distance from the nucleus, right? The outer electron is further away from the nucleus, so it's easier to remove. So I think if you look at group one, hydrogen. So hydrogen, if we look at group one, it will be the most difficult to remove that one electron, the only electron on a hydrogen, because it is very, very close to the nucleus because that's in a 1s shell. But then if you go to lithium, now we're taking an electron away from a 2s shell. It's further away. It's in a higher n quantum level, so it becomes easier. So you see the value of the first ionization energy, which is in kilojoules per mole. It becomes easier. And then if you keep going down the group for sodium, right? For sodium, it's even lower at 490. Potassium's even lower, rubidium even lower, and then finally cesium, which has the lowest first ionization energy of this whole group. It is the easiest to remove the outermost electron of a cesium because that outermost electron is a 6s electron. It's the furthest away from the nucleus. It doesn't feel as much of the positive charge from the nucleus, right? And then so going across the period from left to right, the it typically is more difficult to remove an electron. So ionization energy tends to increase going from left to right, and that is because effective nuclear charge increases from going left to right. So let's remember these trends. Because they apply to both radius and ionization energy. So here, what did I write? Effective nuclear charge increases going from left to right, so electrons are held more tightly and are therefore harder to remove. So let's look at period two. Here we go from boron. If we go from boron to neon, you see that it does increase. The energy to remove that outermost electron increases because effective nuclear charge increases as well. Because every time we go across every element here and we add another electron, we're adding an electron to the 2p orbital. Those electrons in the 2p shell don't shield one another. So Z effective increases dramatically as you go from left to right. So therefore, it becomes more difficult to remove an electron. But if you look closely here at all of the different values going across, so they do tend to increase. So we have boron is 800, carbon is about 1,000, 1,400 for nitrogen, but then for oxygen it kind of dips a little bit. So it goes from 1,400 to 1,300. So from going from nitrogen to oxygen, it actually decreases. But I just told you that ionization energy follows Z effective, right? And ionization energy should increase from going from left to right. But in this instance, it decreases from going from nitrogen to oxygen. But then if we go from oxygen to fluorine, it increases again. And then fluorine to neon, it increases again. So what explains this decreasing, right? Oh, I'll note, so also I have a note here that metals tend to have low ionization energies. So it's a lot easier to remove an electron from a metal. When you remove an electron from a metal, it produces a cation. That's why metals tend to produce cations versus our nonmetals here. It usually takes a lot more energy to remove an electron to form a cation. That's why nonmetals tend to form anions instead of making cations. So this is a reason, our ionization energies is a reason why metals form positive ions. So that's just a little aside. But let's talk again about why nitrogen, going from nitrogen to oxygen, why there is a decrease. And you actually also see the decrease here. So if we go from phosphorus to sulfur, you also see a small decrease. From arsenic to selenium, you also see a small decrease. So why? All right, so So here's the same data just represented in a graph form as we're increasing our atomic number. So what you actually see when we go from lithium to neon, right? I already talked about this, that you would expect a general increase in ionization, except we see that nitrogen has a slightly lower ionization than oxygen, or sorry, nitrogen has a slightly larger ionization energy than oxygen, and also beryllium has a slightly higher ionization energy than boron. So let's just look at those numbers here. So beryllium has a slightly larger ionization energy than boron. All right, so let's talk about why. These irregularities in the ionization energies are related to electron configuration. So remember back in the I think what chapter five we talked about electron configurations. So let's think about what electron are we removing from that element to produce a cation. So if we know what electron we're removing, that might help us explain these anomalous numbers. So I think for beryllium, when we compare beryllium and boron, why beryllium has a slightly lower ionization energy, this one's a little bit more straightforward to think about. So if we write, whoopsie, oh no. So if we write out the electron configuration for beryllium, uh, so we can write the noble gas configuration, right? So the closest noble gas to beryllium is helium. And then to get to beryllium, we fill our 2s orbital with 2 electrons, right? So when you pool, so if we're doing an ionization energy, remember, so ionization energy is the energy to remove an electron. So let's just remember that. So if we want to remove an electron, we're not going to remove it from this helium, the helium core, right? That those are the inner shells. So we're going to remove an electron from its outermost shell, its valence electrons. So the only valence electrons that we have are these 2s, whoops, 2s, this 2s orbital. So if we would write the new electron configuration for the cation we form when we remove that electron, right? So we're removing an electron from the 2s orbital, so that leaves a 2s1. So we're removing one of the electrons, and now we have this extra electron. So we removed an electron from this filled 2s orbital. It's completely filled. So this is going to actually require a lot of energy to remove from a filled shell. So we can compare this to boron. So if we did the same thing for boron, so boron, its electron configuration is helium, 2s2, 2p1. So if we removed an electron to produce a beryllium cation, or sorry, a boron cation, we would remove this electron, the 2p electron. So that 2p shell is not completely filled. So it's going to actually take a lot less energy to pool an electron because it's just like a lonely dangling electron hanging out in a p orbital. So the electron configuration for the cation would be helium 2s2 plus an electron. So in boron, this electron is easier to remove. All right. So, and that is reflected in the value of our ionization energies for beryllium and boron. So this is it's the 2s is already filled, so it's going to be a lot harder to remove. The first ionization energy of beryllium will be larger than for the first ionization energy of boron. Or what did I just say? I just said the first ionization energy of beryllium will be larger than the first ionization energy of boron, because for boron you're removing a lonely electron in the 2p shell. All right. So because beryllium is filled, there's one electron spinning up and one electron spinning down. Right. So you'll have to remove those two electrons are essentially happy in that filled shell. So removing one will take a lot more energy than removing this lonely 2p electron. All right. So that one's pretty straightforward. So then what about oxygen and nitrogen? Why is there a difference there? Again, we can use the same type of reasoning. It's best if we just write out the electron configurations. So for nitrogen, it will be neon, wait, no, helium. Helium, and then 2s2, and then a 2p3 for a nitrogen atom. And so if we remove an electron, we're going to remove an electron from its valence shell. So we're probably going to remove an electron from this 2p orbital. So, whoops. So the new electron configuration for our cation will be 2s2, 2p2 plus an electron. So the reason why nitrogen has a larger first ionization energy than oxygen is because, let's see a different color, because 2p3, this is a half filled electron, or orbital, because there's 3 electrons in the p shell. You know, we can draw it like this, 3. So there's some stability here when it's half filled. So it will be a lot more difficult to remove this electron because they're all spinning in the same direction. So we can compare this to oxygen. Oh, I did not give myself enough room. So if we did this for oxygen, so oxygen, its electron configuration is helium, 2s2, 2p4. And so if we make an oxygen cation, remove one of those electrons. Now let's compare our half-filled nitrogen example to oxygen. We're going to remove one of the 2p electrons. So if I draw out the electron configuration here and follow Hund's rule, so you can see here that we're actually we can remove this one lonely electron that's spinning the opposite direction as the rest of them. So this different color. This electron is easier to remove than this electron in the nitrogen half-filled example. This is harder to remove. So this brings us back to the stability of both filled orbitals and half-filled orbitals, and how that relates to ionization energy. All right, so moving on. So when talking about half-filled and filled orbitals, you can kind of see through the values the stability of these different configurations. So all of the transition metals at the end of the D block, they have completely filled D10 configuration. So this is this group 12. So all of the elements, zinc, cadmium, mercury, these all have D10 electron configurations, right? So this is starting at scantium. This is the whole D block. So zinc, cadmium, and mercury, they all have the highest ionization energy within the D block series. So to remove an electron from a zinc atom is much more difficult than removing an electron from a scantium atom, because you can kind of think of it this way. Oops, this needs to be bigger. 2, 3, 4, 5. Yeah. So for scantium, right, there's just one electron in the D shell, versus for zinc, you'll have, this will be all filled. Everything will be, this doesn't look that great. Everything will be filled. So it will be much easier to remove this lonely electron, easier to remove, than a completely filled D10 block, because everything is paired. So you'll have to break up one of the pairs in order to remove. Harder. All right. So I think if you write out the electron configuration, using the boxes, you can kind of see which electrons will be harder versus easier to remove. And then finally, if you look at the whole series, the largest ionization energies for any given element they're going to be in the noble gases. Gases have the highest ionization energy. That kind of makes sense. We always talk about noble gases, they don't react, right? And the reasoning is because it takes a lot of energy to remove electrons. So reactions typically have, transfers of electrons are happening to some extent. So because all of these noble gases, they have really large ionization energies because they have completely filled S and P subshell. So it's going to be really difficult to remove any of those paired electrons, because they're all paired, they're all happy, or they're all stable, essentially. And so that's why noble gases tend to not be reactive at all. But you can still see that the trend with ionization energies going down a group follows with noble gases. So within the noble gases, you see that because our distance from the nucleus increases, that it does tend to become easier to remove an electron going down the noble gas series. So you typically won't see like any molecules that contain a helium because helium doesn't want to give or share any of its electrons, right? You tend to not see molecules with neon or argon; those are inert gases, they're noble gases. But you see, as we go down the group, it does tend to get easier to remove an electron. And actually, once you get to xenon, you do actually see different xenon compounds. They're hard to make, but you can make them, and people have isolated them, different xenon um, compounds, because it is a lot easier to remove an electron from xenon versus a helium atom. So that's just my little aside there. All right, so that is ionization energy. So that's removing an electron, making cations. So on the flip side of things, we have to talk about electron affinity, which is just the opposite. So electron affinity is the energy associated with adding an electron to a gaseous atom, neutral atom, or ion. So, okay. So remember, ionization energy is removing an electron. Electron affinity is placing or adding an electron onto an element. So here I have an example. We can take a chlorine atom and add an electron to give our chloride um, anion that we typically see in ionic compounds like sodium chloride, right? So we have chlorine becoming chloride, becoming a charged ion. So the associated electron affinity here, so I have a value here, it's negative 349 kilojoules per mole. So you see here that for electron affinity, that at least for this specific example, electron affinity is negative. So let's think about our negative and positive signs relating to energy. So since this is negative, this means that energy is being released. All right. So typically with electron affinity, energy is released when electron affinity is negative. So why is this negative? Why did it require energy to remove an electron from an atom? But and then why for electron affinity um, are we releasing energy? Well, it's because when we bring an electron in the vicinity of a positive nucleus, there is an attraction. So there's a stability when we bring an extra electron to the atom. So energy is released because now this chlorine is becoming more stable as a chloride. So chloride is more stable than just a lonely chloride. We don't typically see chlorine just Cl out in nature. If we see a chloride atom of some sort, it's going to be a chloride. All right. Okay, so trends in electron affinity parallel those in atomic radii. So if we can get an electron closer to the nucleus, remember it's positively charged, an electron is negatively charged. So if we can bring those charges closer together, you will get a more negative ionization energy, or you can think more energy will be released when a positive charge and negative charge can get closer together. Let's see if I can write something. So if we have, something like A and we're adding an electron and making A minus, this A minus will be more stable when the electron and nucleus are close together. That's the general trend. So if we look at the trends with electron affinity in this chart, you can see, so maybe I should add more stable when the electron and nucleus are close, meaning that electron affinity is more negative, or more energy is being released because A minus is much more stable than A. So let's see if we can't find some trends here. So if we just look at group 1, hydrogen. So if we want to make an H minus ion, we would be adding an electron to the 1s shell. So that's as close as that electron can be to the nucleus, essentially. Versus if we look at cesium, if we add an electron to make a cesium minus, we would be adding it to a 6s shell. Whoops, you can't see that, can you? No, you can't. a 6s shell. Versus, yeah, like I said, hydrogen, you're adding it to a 1s shell. So you can see the electron that we're adding to hydrogen in the 1s shell is closer. So electron affinity is much more negative for hydrogen. Versus for cesium, if we're making a cesium minus, we're adding it to a 6s shell, it's much further away from the nucleus, so we don't get that electrostatic stability that we would get for a hydrogen um, negatively charged ion. So if we compare forming a hydrogen anion versus a cesium anion, you can see since we're adding an electron um, for cesium, it's further away from the nucleus, so we don't get as much energy back. So in general, overall, different color. Whoops. Electron affinity increases or becomes more positive as you go down a group. So remember I said that electron affinity closely resembles atomic radius. So remember when we said that radius will increase going down a group, so electron affinity also increases as you go down a group. Or electron affinity increases or becomes more positive as you go down a group. So if we look from left to right across the periodic table, remember radius decreases as we go left to right. So decreases. So electron affinity also decreases as you go left to right. Decreases or becomes more negative as you go from left to right across the periodic table. So you can see fluorine, and then our exceptions are the noble gases, but you can see fluorine is very highly negative. So electron affinity decreases. So as you go from left to right. So lithium has a much lower or much higher electron affinity than fluorine is much more negative. All right. But there are some exceptions. So if you look here, you'd think that fluorine would have the lowest or most negative electron affinity, but it doesn't. It's actually chlorine has the most negative electron affinity. So let's talk about why. So some of the exceptions with electron affinity, for the most part, it resembles that of the atomic radii, but the exceptions is fluorine. So fluorine is the smallest halogen, so you would think that bringing an electron to that halogen, since it's the smallest, would result in the most energy stability, and then that would give us the most negative electron affinity, but that's not the case. If you look at fluorine and chlorine, chlorine to become a chloride actually has the most negative electron affinity. But the reasoning that chlorine has the lowest electron affinity is because with fluorine, when you bring that electron in to that inner shell, that second period element for fluorine is so small that when you add an extra electron, there's actually some repulsion there from the n equals 2 shell. And so that repulsion actually counteracts the stability given when you bring an electron and the positively charged nucleus together. All right, so just remember that chlorine has the lowest electron affinity. All right, and then the other exception is noble gases. They have positive electron affinities. So remember what positive means in terms of energy. So if the energy is positive, that means it requires energy to add the electron, because we're talking about electron affinity. All right. So noble gases have a positive electron affinity because it's very difficult to add that extra electron. Noble gases are already content and stable as they are. They don't want to lose electrons. They don't want to gain electrons. All right. So that positive energy means that there's no energy benefit from them gaining an electron. And then also the other exception is that 2A, group 2A, so that's the alkaline earth metals. Also, so this is 2A. So beryllium, magnesium, calcium also have positive electron affinity values, and that's because we're, again, just like the noble gases, we're trying to add an electron to an already filled subshell. So the 2A elements already have a filled s orbital, and they don't want to gain another electron, that it's going to take more energy to add an electron to a new shell. Right? And then the those two groups are already happy as they are. They don't want to gain any more electrons, so that's why those electron affinities are positive. And then finally, the last exception is group 5. So these electron affinities are less negative than expected, and this is kind of a similar reason to our ionization energies as before. So if we look at the 5A group, so that's the nitrogen group, right? 1, 2, 3, 4, 5. Yep. So these values are less negative, or you can say more positive than expected. So you can again think about, we have a half-filled shell already. So nitrogen will already have a what's it? A 2s, sorry, 2, yeah, 2s2, 2p3 subshell. So helium. So this is for nitrogen. So if we drew that, so here is our p subshell. So this is a neutral nitrogen. So if we wanted to add an electron, we would have to start pairing, essentially. That we would have to put an electron with an opposite spin. So there's a little bit of repulsion there. So you're not getting as much energy stability, because now you have to essentially break that half. Nitrogen is already half filled, so you'll have to break it. So that's why electron affinities for the group 5 is slightly more positive or less negative than anticipated. Again, these are the same reasons we kind of talked about for ionization energy. So it still holds true. So you have to think about half filled versus completely filled, what energy is required to break it, to break the stability given when you have a fully filled or half filled orbital. All right, so what did I actually write for my reasoning? Adding an electron to a relatively stable half-filled p subshell, it requires more energy to essentially uh, break that half-filled subshell. Okay, great. All right, and so now let's talk about electronegativity, since we're already talking about electrons. So electronegativity, let's define that. So we are defining this, defined as the attraction of an element for electrons in a chemical bond. Or you can think of electronegativity as the tendency for an element to gain electrons. So the trend with electronegativity in the periodic table is that so fluorine is the most electronegative, and then cesium, which would be here on our generalized periodic table, this would have the least, would be the least electronegative. So this really kind of relates directly with electron affinity. Fluorine is the most likely to to have electrons near it, while cesium is the least likely to have electrons being added to it. So with this, we use the Pauling scale. Um, so it's just a number. So in this case, fluorine we just define as having the most electronegative and has a value of 4.0. So this trend relates to the Z effective that we already talked about, effective nuclear charge. It's the attraction the electrons feel with that nucleus, depending on where that electron is. And we use electronegativity a lot when talking about reactivity and chemical bonds, and it's much more practical to talk about atoms in terms of electronegativity than in terms of ionization energy or electron affinity. So in your course of chemistry for the rest of time, you'll probably be talking about electronegativity when comparing different atoms, because we're typically talking about atoms when they're bonded in molecules instead of just individual atoms in the gas phase. So talking about electronegativity is just a much more robust definition that we use. So here is a chart for all the different Pauling scale, remember Pauling scale, electronegativities. All right, so these are just numbers. Can I zoom in on that? All right, so we can see we defined fluorine as having is the most electronegative, while cesium or francium, there's not a lot of francium on Earth. More likely to see cesium though. That cesium and francium have are the least electronegative. All right. So you can see the trends when we talk about metals versus nonmetals. You know, the metals over on the left side of the periodic table, let's do a different color. The metals on the left side tend to have very small electronegativities, which just means that electrons don't tend to, associate with these types of atoms or metals. We don't typically see metals as anions with extra electrons on them. But if you look on this side of the periodic table where the nonmetals are, you can see that they're much higher. They're, at least in the, twos, ones and twos on the Pauling scale. So you can see that nonmetals tend to have electrons associated with it. So nonmetals are much more electronegative because electrons are more likely to be on them. So that kind of brings us into what makes things. Why do we call the metals metals or have metallic behaviors, and why do we call the elements on the right side nonmetals? Why are they, what defines non-metallic character? So let's talk about that. So, we've talked about metals and nonmetals a lot lately, in the past, over the past semester. Um, so, we've kind of loosely talked about, where the metals are. Metals tend to be on the left side of the periodic table, while nonmetals tend to be on the right side of the periodic table. So let's just define that now. So metallic behavior increases going from right to left on the periodic table, while metallic character also increases going down the periodic table. So you can kind of, if we look at the periodic table, this side where cesium is the most metallic, while the helium side is the least metallic. And then, of course, our metalloids, these purple guys, these are our metalloids because they're kind of between the nonmetal and metallic side. And they're typically defined on the periodic table for you. Excuse me, for you. Okay, what am I talking about next? Okay, so there's that trend that you can see, that metallic character increases going from right to left, and then metallic character also increases going down the periodic table. So let's actually define what metals versus nonmetals are. So this is going to be a lot of writing. So what metallic character are we talking about? So things that define metals. Typically, metals have low electronegativities. We already know that. Low electronegativities. So electrons do not typically associate themselves with metals, right? Metals do not tend to make anions. So a low electronegativity. So yeah, typically we um, call electronegativity En. So a low electronegativity means that you will typically form cations instead of anions. Cations, so remember those are positively charged, not anions. Because the electronegativity is low, electrons do not typically associate themselves with metals. Typically, with metals, electrons are removed instead of added. All right. Another element of metallic character is that their oxides are typically basic. And I will describe that in another slide. And their hydrides are ionic in character. All right. So an example would be like sodium hydride. All right. This is because hydrogen is more electronegative than metals. So I might have to go back a couple slides to show you this. Okay. Yeah, I forgot to mention this, that hydrogen here on our Pauling scale of electronegativities, so you can kind of see that hydrogen is out of place, right? Hydrogen usually is here on the periodic table, but when it comes to electronegativity, hydrogen has a Pauling scale of 2.1 versus like sodium has a Pauling scale of 0.9. So if you compare the value 2.1 versus zero 0.9, hydrogen is much more likely to associate itself with an electron. So you are more likely to make a H minus ion than an Na minus ion. So that's why when you produce a hydride, if you put together a hydrogen and a metal, that the hydrogen is more likely to gain an electron and you'll make an ionic compound. right? And that's what that means. Hydrides are ionic in character, so our sodium is going to lose an electron, and hydrogen's going to gain it to make a hydride. And I will compare this with nonmetals because it's not the case for nonmetals. Okay. Yeah. All right. So for nonmetals, nonmetals have high electronegativities. So En. So that means, large electronegativities means that nonmetals are more likely to form anions, which are negatively charged, right? So not cations. Because its electronegativity is high, its nonmetals are much more likely to associate with an electron, or an electron is more likely to associate with a nonmetal versus a metal. What else? So for nonmetals, their oxides are typically acidic. So this contrasts itself with metals, and I'll show you some examples in the next slide. And then finally, hydrides are molecular. So for example, CH4. So carbon is a nonmetal. So if you make a compound with carbons and hydrogens, you're going to make a molecular compound. So CH4, which has covalent bonding, which we'll talk about next chapter. So instead of having a transfer of an electrons like for our sodium hydride example, where hydrogen is much more electronegative, so it's more likely to gain that electron from sodium. If we compare that to a nonmetal plus hydrogen containing molecule, that molecule will be molecular. So those electrons will actually share with one another. And the reasoning here, to write this, it's because hydrogen is generally less electronegative than nonmetals. Or their electronegativities are the same. So there's not a driving force for an electron transfer to happen. So instead, electrons are more likely to share with one another. Atoms are more likely to share those valence electrons with one another to produce covalent bonding. Okay, and then what do I say here? That cesium is generally considered the most metallic element. So we kind of know that from our from this chart up here, that we typically call cesium the most metallic element. But you see that francium is actually, in the cornermost. But the thing is that there's like not a lot of francium on the Earth, and it's not studied too often. And on top of that, it is radioactive. So you might have a very metallic francium sample, but in a couple weeks, that francium might be something else, some other element, because it's radioactive. All right, so yeah, in general, cesium is considered the most metallic element. Okay, so diving deeper into metals, we've already kind of done this, but we can predict the charge of the cation that is produced when you have a metal. Oops. With main group metals. So that means, group 1 and group 2 with those different metals. So when we look at group 1, the alkali metals, the charge of those ions is equal to the group number. So we already know that. Oh, here's my periodic table. That in group 1, lithium, sodium, all of these elements produce +1 cations. All right, and the same thing with group 2. Group 2, beryllium, magnesium, calcium, all of those elements produce 2+ cations because for both of these examples, they lose their valence electron shells. But then when we can also predict some of these metals on the side of the periodic table too, like aluminum. Where's aluminum? Aluminum typically produces a 3+ cation because, again, we lose all of its valence shell electrons, and same thing with group 4 and 5. But when we get to this side of the periodic table, it kind of gets funky. So if we look at our aluminum example, so aluminum will lose all of its valence electrons. So it's what is that? Our 3s2 and 3p1. So we will lose all of those electrons to produce a 3+ cation. Gallium. So if we just go down the group, gallium can also lose all three of its 4s2 and 4p1. So 4s2 3. Whoops. 4p1 electrons so we can lose all three to produce a +3 cation. But for at least for gallium, there are also +1 gallium uh, compounds with a gallium +1 um, cations associated with it. So we could either lose just the 4p electrons, or we can lose all three. So it is possible we can get either a +1 gallium or a +3 gallium. So we can lose both. But for aluminum, typically when you have an aluminum compound, you lose all three. But for gallium, you can either lose one or all three. And so you can see where that one comes from, that you're most likely to lose that 4p, that lonely 4p electron to produce a gallium plus one. All right, so if we actually continue down the group, under gallium is indium. So indium, if you're going to see an indium ionic compound, it'll actually probably most likely be an indium +1 compound, but also indium +3 exists. So it's kind of um, the same type of uh, thing going on here, where we can have indium is 5s2 or and 5p1. So indium is most likely to just lose um, one of its p electrons to produce an indium +1, or it can lose all three. There are some instances where we have an indium +3 compound and it will lose all three of those electrons. And then finally, under indium is thallium. So for thallium, only +1 electron, only thallium +1 compounds exist. So this can easily be explained by so it's 6s2 and 6p1. So this is a product of relativity. So actually what you're seeing is the inert pair effect. So for thallium, you're only going to lose one electron to produce the +1, to produce thallium +1. Okay. So that is the charge trend for group 3, where we can have either a +3 or a +1 charge going down the group. But this trend also happens in our fourth group, group 4 and group 5. So maybe I will summarize this. So for the third group, we can either have a +1, +1 or a +3 charge. For group 4, we can have a +2 or a +4 charge. And then finally for group 5, we can have a +3 or +5 charge. And the reasoning here is for the two different charges is either you lose all of the valence electrons, or you just lose the valence p electrons. So that's what the meaning here is. And so I went through all of the different examples for the third group. So maybe on your own time you can kind of use the same type of uh, analysis for our fourth group and our fifth group to see which electrons are being removed to produce either a 2 and 4 plus cation, or a 3 and 5 plus cation for our fifth group. All right, moving on. Okay, so let's talk about reactivity of the main group elements. So in general, it becomes easier to lose outer shell electrons as we go down the group in the periodic table. So we know that the radius gets larger, it's easier to pluck off an outer shell electron because n increases as you go down the group, and so outer shell electrons are further away from the nucleus. So with main group chemistry, since it's easier to lose an electron, so reactivity of main group elements, main group metals, so we're talking about metals. And so I'm talking about groups 1A and 2A, tend to increase as we go down a group. So the alkali metals, or group 1A, are the most reactive metals because they only need to lose one electron to get that stable noble gas configuration. So lithium, sodium, potassium, rubidium, and cesium, they all have a single s electron in their valence shell. So some pretty cool things. If you ever see, I think I might post a link to some YouTube videos of folks throwing these different alkali metals into water. So these different elements are very, very reactive with water. Am I going to talk about that? Yeah, yeah. So in this slide, so group 1A alkali metals, they react violently with water. So if you add the metal to water, you will get the metal hydroxide and hydrogen gas. And so the reactivity of these different materials increases, gets more violent. Violence increases as we go down the group. So I'll include the link to a cool YouTube video that showcases all of the different elements when you chuck them into water. So reactivity for group 1A, the alkali metals, increases. Activity increases as we go down the group. All right. So next, let's talk about group 2A, the alkaline earth metals. So that's beryllium, magnesium, calcium, strontium, barium. So all of these have 2 electrons in their valence shells. So because there's 2 electrons in the s orbital, so it's completely filled, the group 2A is much more stable than the alkali metals. The alkaline earth metals also have higher densities and melting points than alkali metals. Their ionization energies are low, so the energy required to remove an electron is low, but not as low or not as easy to remove an electron as alkali metals. And again, this has to do with we have a filled s orbital here. So these group 2A metals are not as reactive as alkali metals, but as you go down the periodic table of the 2A elements, you do see reactivity increases as we go down the group. What did I want to say? So yeah, but they're not as reactive as group 1A, but they're still somewhat reactive in themselves. So just to summarize, so lower reactivities compared to the alkali metals, the 1A group. They're not as reactive with water. Usually you have to add some type of energy into the system to get them to react. So here I just kind of like summarize it. Beryllium doesn't react with water. Magnesium will react only with steam. So if it's H2O gas, so if there's a lot of heat available, then magnesium will react. And then all the other alkali earth metals do react with water. So you can kind of see the trend here. Beryllium, unreactive, but as you go down the group, reactivity does increase because if you chuck these materials into water, they will react. So you do see the trend within the group that reactivity does increase as you go down the group because you're becoming more metallic in character. Increase as you go down the group. Great. So you can kind of see like that with magnesium, it will only react with like hot steam. And then if you just go one element down to calcium, solid calcium will just react with plain old water. And same with strontium, barium, and radium. Okay, great. Okay, where are we now? Okay. So something that we've talked about, a lot is that compounds when the different types of compounds that are formed. So if we bring a metal and a non-metal together, you will produce an ionic compound. And the reasoning here is because metals have low ionization energies. So it's quite easy to grab an electron off of a metal, while nonmetals have high electron affinities, so they are more likely to gain electrons to form anions, while metals produce cations because of their low ionization energy. So these two characteristics paired together is what favors the formation of an ionic compound. So that's why electron transfer happens. Essentially, the metal loses an electron because it's quite easy to lose an electron, and then that nonmetal gains an electron because of its high electron affinity. And so that's why this transfer of an electron happens to form an ionic compound. All right. Okay, so that kind of explains, why I just always told you that, you have to have a metal and a nonmetal to make an ionic compound, and then, a nonmetal and a nonmetal to produce a molecular compound. So this is the explanation of why you have to have a metal and a nonmetal to produce an ionic compound. Okay, so I told you that I would explain why oxides, the oxides and basic versus acidic stuff. So generally, oxides of metals are basic. So the general formula is a metal oxide plus water gives you a metal hydroxide. So I'll give you an example. So if I have a metal oxide, so let's just say calcium oxide, solid, plus water, so H2O, liquid, gives us a metal hydroxide. Is this balanced? Yeah, 2. So remember, hydroxide is together is a -1 charge, and a calcium as a cation has a 2 plus charge. So there has to be 2 hydroxides here, and you will get aqueous. So we know that calcium hydroxide is a strong base because it contains a um, anion. So this is a strong base. So this is what I mean when I say that when we have a a metal oxide plus water gives a metal hydroxide a strong base. So metals are that's the reason why metal oxides are basic, because when you add them to water, it creates a strong base, strong base, strong base. All right. So since metal oxides are basic, that means you can neutralize them with acid. So instead of chucking a metal oxide into water, we can chuck it into acid. And since we know metal oxides are basic, this should in turn produce a neutralization reaction, which it does. So if we take a metal oxide plus an acid like HCl or nitric acid, something like that, anything with a proton, or sorry, a hydrogen cation associated with it, a neutralization reaction should occur. And so we know that neutralization reactions result in a salt plus water. That neutralization reactions are a double displacement reaction where the driving force is the formation of water, right? So formation of water is our driving force for this double displacement reaction, driving force. So my example here is a different metal oxide, so nickel oxide. Nickel is a metal, oxygen, so nickel oxide is a metal oxide. We can add nitric acid to it, and we will produce nickel nitrate and water. So when you put, what's it? So this example of nickel oxide is insoluble in water, but it's still considered a basic metal oxide because it will react in acid. So what you see here, nickel oxide is like this dirt-looking stuff. All right, so this is kind of before and after. So if you chuck some nickel oxide into these beakers one contains acid, the other just contains water. So what you see here is when you put nickel oxide in water, that nickel oxide is insoluble in water, so you just see dirt hanging out at the bottom of the beaker. But when you put nickel oxide in acid, such as nitric acid, you see that the nickel oxide dissolves in the acid because it's a basic metal oxide, and essentially the nickel oxide becomes neutralized by the acid, and we produce the salt nickel nitrate, nickel 2 nitrate, and water. So this is evidence that the dissolving of nickel oxide in acid indicates that nickel oxide is a basic metal oxide. All right, because not all metal oxides are soluble in water, so this is just more evidence that metal oxides are basic since they can dissolve in acid. Okay, so moving on. So let's move on. So we talked about metals. Let's talk about nonmetals. So on the right side of the periodic table, we have most of the nonmetals. Nonmetals tend to be gases or dull, brittle solids that are poor conductors of heat and electricity because they are not metallic. All right, so bromine is the one unusual thing of unusual cases of the elements. It's one of the only few elements that is a liquid at room temperature. So the only other element that's a liquid at room temperature is mercury, which is a metal. But in general, most of the nonmetals naturally occurring are either solids or gases at room temperature. So here are some examples. So chlorine is a gas, bromine's a liquid, iodine is a solid, elemental sulfur is a solid. All right. So we talked about compounds of metals. So when you combine a metal and a nonmetal, you get an ionic compound. Well, if you make a compound that only contains nonmetals, you produce a molecular compound. We kind of already knew that from our naming convention things. So we'll discuss more chemical bonding. We'll kind of dive deeper into the different types of um, uh, bonding descriptions when it comes to ionic compounds versus molecular compounds. But like, let's just recap. That molecular compounds um, share electrons when formed. So remember, molecular compounds are between nonmetals, and then ionic compounds form with an electron transfer. So we produce a cation, an anion, and this is because we have a metal and a nonmetal. And our reasoning here is because metals have low ionization energies and nonmetals have high electron affinities. So we already talked about that, but this is just like a nice recap. And because of that low ionization energy and high electron affinity, it's very favorable for an electron transfer to occur. So we have a cation and anion producing an ionic compound. All right. But going back to molecular compounds, so for molecular compounds, there's not enough difference in the attraction of electrons between nonmetals. So electron transfer is not favorable. If you look at the electronegativities, there's not much of a difference between all of the different nonmetals. So instead of transferring electrons, they share electrons instead. So this is called covalent bonding, and we'll get more dive deeper into it in chapter 7. But for molecular compounds, there's sharing of electrons, the formation of covalent bonding, while in ionic compounds, when we have an electron transfer and electrostatics is what are keeping the cation and anion together, that's an ionic bond, versus molecular compounds have covalent bonding. And so here is an example. So covalent bonding is what dominates organic chemistry when you get to it, next or 2 years from now or wherever. So here is an example. We have aspirin, which has carbons, hydrogens, and oxygens in its molecular formula. So carbon, hydrogen, and oxygen are all nonmetals. So all the bonding in this example molecular drawing is all covalent bonding, because carbon, hydrogen, and oxygen, they're all non-metals. Great. Okay, so let's talk about non-metal oxides. So remember, metal oxides are basic, non-metal oxides are acidic. So here is an example. So in this photo, in this beaker, or sorry, in this wire, I don't even know why they're using a graduated cylinder, but there's an indicator in this vessel. So you guys used indicators with that the one molar mass of an unknown acid lab. So this indicator, bromothymol blue, is initially blue, meaning that the solution, it might just be like water or something, is slightly basic. But when you add this is dry ice, which is just CO2 in its solid form. That's what dry ice is. Um, when you drop dry ice into the water with the indicator in it, it turns yellow, which means that now this solution is acidic. So so before you drop the dry ice in, it's essentially neutral or basic, the solution, before you drop the dry ice. But then once you drop the dry ice in, it becomes acidic because the indicator turns yellow. So what you're seeing is a solution of carbon dioxide in water. So when you stick carbon dioxide in water, you produce what's called carbonic acid. So you're forming an acid. So CO2 is a non-metal oxide, if you couldn't tell by its molecular formula, but I didn't state it right off the bat. But so CO2 is a non-metal oxide. So when you stick it into water, it produces carbonic acid, which is acidic, and it will turn the indicator, in this case bromothymol blue, yellow, because it's acidic. And so this is kind of why when you drink soda, why they say soda is so bad for your teeth, because it's acidic. Well, what makes soda yummy, I guess, is all the dissolved CO2, um, making the fizzy, bubbly soda that we love. But with all that dissolved CO2 in the liquid, it also produces a very acidic environment solution. And so that's why you can either feel a burning sensation in your throat if you drink soda too fast, or you can think soda is super acidic, so it'll dissolve your teeth, or if you drink a bunch of soda, it might give you a stomach ache. So those are all indications that CO2 is acidic. Okay, so some other examples of acidity when it comes to nonmetals. So here are some examples. So just like with nonmetals, or sorry, with metal oxides, if we take a metal oxide, sorry, if we take a non-metal oxide, so in the previous example, we talked about CO2, which is a nonmetal oxide. So another example of a nonmetal oxide is SO3. Um, plus water will give us an acid. So remember before with metal oxides, it was metal oxide plus water gave us a metal hydroxide or a base, but now this time non-metal oxide plus water gives us an acid. So this is an example. So SO3 in the gaseous form plus water gives us sulfuric acid, H2SO4. So oxides of sulfur and nitrogen, which typically comes off as we drive our cars off of our exhaust pipes. So like NOx is in SOx. These are oxides of nitrogen and sulfur come off of our car exhausts. So this is what produces acid rain. So they say, smog or, all of the byproducts of engines, cars, and industry can produce acid rain because essentially what we're doing is we're making a bunch of non-metal oxides, putting them in the air. So when moisture through rain or whatever comes down through the atmosphere and combines with these non-metal oxides that are in the air, we produce acid rain. So when we have SO3 combining with water, we make sulfuric acid. When oxides of nitrogen combine with air, we produce nitric acid. So those are the constituents of acid rain from the oxides of nitrogen and oxides of sulfur combining with water to produce sulfuric acid and nitric acid, right? And so I guess we can counter that every day. And so yeah, so this picture is actually an example. So here is a statue that was probably built a very, very long time ago. So statues are just minerals, right, or made of rock or like chiseled from rocks or marble. So over time, this statue underwent, I guess acid rain, and slowly the facade of the statue deteriorated from acid rain over time, and it just essentially dissolved the face and all the features off of the statue. Right, and so similar with metal oxides, acidic non-metal oxides can also be neutralized. So since non-metal oxides are acidic, we'll have to um, neutralize the acidic non-metal oxides with a base. And again, remember with neutralization reactions, formation of water is our driving force. So here is an example where we have a non-metal oxide, CO2, and we can combine it with any type of base. So here the example is barium hydroxide, but we could use sodium hydroxide, whatever strong base you want, and we produce barium carbonate and water. So barium carbonate is our salt, and then water is our driving force. But again, you could use any type of metal. You can either any type of strong base that you want for this reaction to occur. All right. Okay, almost done here. All right. So for nonmetal ions, remember nonmetal ions. When you're making an ion with a nonmetal, because those electron affinities are high, nonmetal ions will tend to produce anions. Or you can see nonmetals tend to gain electrons or form ions in reactions with metals to get that noble gas configuration. Remember, nonmetals are on the right side of the periodic table, so they're more likely to gain electrons to get that noble gas configuration. So when you see nonmetal ions, we kind of already talked about this. Charges on a simple ion or just a single element ion, nonmetal ion, is predicted by its charge will be equal to its group number minus 8. Oh, I don't want to do that. Okay, so, or I always like to just look at where those nonmetals are on the periodic table and just count how many spaces to achieve the noble gas configuration. So you can see oxygen, you need to jump 1, 2. So you'll typically produce an oxygen 2 minus anion. But if you want to use this this formula that the charge of a nonmetal is equal to its group number minus 8, you can use the same formula. So oxygen is group 6. So group 6 minus 8, so 6 minus 8 equals -2. So that's the charge of oxygen. But you can do anything. So let's say bromine. So if we wanted to make a bromine ion, we would take the group number minus 8. So group bromine is in group 7. So 7 minus 8 is -1. So a bromine ion would be Br minus 1, or bromide. Right? So here is a formula to remember that, to know what are the common charges of nonmetal ions or anions. So again, the reasoning for this formula is 8 is the number of electrons held in the valence s and p subshells of a noble gas. So we just want the nonmetal wants to achieve its noble gas configuration, so it will gain that many electrons to do so. So you can think, okay, let's do some examples. What ions do you predict will be formed with the following nonmetals? So for iodine, or I, so if we actually use the formula here, so iodine is group 7. So 7 minus 8 equals -1, so we will produce an I minus anion. So nitrogen is group 5. So 5 minus 8 equals -3. So nitrogen, if it were to form a simple anion, would be a N 3 minus. Right? And then selenium. Selenium is group 6. I'll just write that group. Group 6, so 6 minus 8 equals -2. So selenium, 2 minus. Anions. And so see, all of these examples produce anions because they are nonmetals. Okay. Oh yeah, here. So formation of anions is typically a non-metal property. Yeah. All right. Last but not least, metalloids. The weird ones, the weird cousins of all the elements. Okay. So metalloids have properties that are both between true metals and nonmetals. That's why they're called metalloids. So metals are good conductors of electricity. Nonmetals are bad conductors of electricity. They're typically insulators. So you would predict that metalloids would be not like kind of in the middle, like okay insulators, okay conductors, and that's exactly what they are. They actually have semiconductor properties. So for example, silicon, which is in this picture, looks shiny like a metal. So right, it's shiny like a metal, but it's brittle like a nonmetal. It's not a great conductor, but it's a semiconductor, so meaning that under enough stress, it can conduct electricity. Um, so that's kind of a reason why silicon is in the in the metalloid region. It's not a great conductor, but I mean, if you put enough effort in or put enough stress into it, it can conduct electricity. So, we'll talk more about semiconducting properties in I guess in Chem 1220, but just know that metalloids have properties in between that of metals and nonmetals, and that silicon and its semiconductor properties is an indication of that. All right, so metalloids, so you can see that they're found on the periodic table right here in that purple stair step region, and so it's the approximate diagonal where the changeover between nonmetals and metals kind of takes over. So the reasoning why it's a stair step is because remember we get more metallic as we go down. As we go down a group, we get more metallic, but we also get more metallic as we go left to right. We get less metallic. Metallic. And this is more metallic. So because of the two trends going this way and this way, that's why we have the stair step location of where the metalloids are, because we get more metallic as we go down and less metallic as we go this way. But again, all periodic tables kind of mark where the metalloids are, and so if you ever forget, it should always be there. So I think this is the last slide. So trends and properties when it comes to metalloids. So if we put those trends together, so remember that metallic character increases going this way. Sorry, increases going this way, and then decreases going this way. So if we look at some of the trends within the metalloids, bismuth is, so if we compare the basicity of bismuth oxide versus an oxide of phosphorus. So, what did I want to say here? So bismuth, so Bi, so I'll just give you what the oxide of bismuth is. So bismuth oxide is Bi2O3, and the oxide of phosphorus is Oh, I have a, is this, all right. So let me just give you the formulas of bismuth oxide and the oxide of phosphorus. So bismuth oxide is Bi2O3, and the oxide of phosphorus is P4O10. So we want to compare the basicity of these two oxides. So if I remember correctly, that metals, metal oxides are basic. So the more metallic an element is, the more basic it should be, right? So let's compare bismuth and phosphorus. Let's look at the periodic table. So I don't even need to know what the formula of these oxides are. All we needed to know is bismuth versus phosphorus. So if we look at our periodic table, bismuth is, can't do it backwards. Bismuth is here, and phosphorus is 3 rows up. So if we remember our trends, we get more metallic going down. So you can actually see also that bismuth is on the metal side and phosphorus is on the non-metal side. So that's kind of an indication too. So if we remember basicity, metal oxides are basic, so the more metallic, the more basic. So to answer this question, it's not really a question, but let's compare basicity. I would say bismuth is more metallic. So the oxide of bismuth should be more basic. So that's my thought process there. So think about the relative metallicness of the two elements being compared. And since we're talking about basicity, the more metallic one will be the more basic oxide. The more metallic oxide will be the more basic one. All right, so let's do the same kind of comparison with the acidity of an oxide of sulfur versus the oxide of phosphorus. So kind of the same thing. So I like to think, okay, when it comes to acidity, um, the I just think of like the opposite of what we just talked about. So the less metallic element will have the more acidic oxide. So again, I don't even need to look at the formulas for these things. I just know we're comparing an oxide of sulfur and an oxide of phosphorus. So let's see, phosphorus and sulfur, they're right next to one another. All right. So what was the trend? It's we become less metallic going from left to right. So that means that phosphorus is more metallic than sulfur because we're becoming less metallic going this way. So that means sulfur is the least. Oops. Sulfur is the least metallic. So that means the sulfur oxide will be more acidic. So that is my rationale there. And so here I actually just wrote the acid strength. So these are the reactions that are actually happening. So if we wanted to compare the acidity of sulfur, the sulfur oxide and the oxide of phosphorus. So here, this example, I've shown you the molecular formula of the sulfur oxide and the phosphorus oxide. Add them to water. So for SO3 plus water, this produces sulfuric acid. And then P4O10, which is the oxide of phosphorus, which you don't need to know that. But if you add water to it, you actually make phosphoric acid, H3PO4. So if you kind of remember our strong acids, our 7 strong acids, one of them is H2SO4. So H2SO4 is a strong acid, while H3PO4 is a weak acid. So here is another indication of the extent of the metallic character of comparing sulfur and phosphorus. Sulfur is less metallic, so therefore it will be more acidic and will produce a strong acid when compared to phosphorus, which is slightly more metallic. And when you put that oxide in water, it actually produces a weak acid, phosphoric acid. So I will give you guys plenty of more examples to kind of think about trends and chemical properties, but that kind of concludes chapter 6. I will upload a study guide for chapter 6 because this was a very long chapter. So I will give you guys plenty of practice problems for you to work through. And then I guess I will post another video for chapter 7 lecture materials as soon as I get that recorded. All right, thanks for listening, guys.